Have you ever been driving, glanced down at your speedometer, and just wondered, what does that number actually mean? I mean, it's not your average speed for the whole trip, so what is it? Well, today we are diving deep into the physics of right now. We're talking about instantaneous velocity. So, picture this. You're on a road trip, you've covered 300 kilometers in about 5 hours. It's pretty simple math, right? Your average speed was 60 kilometers an hour. But the thing is, that average includes everything. Stopping for coffee, getting stuck behind a slow truck, and that amazing open stretch of highway where you sped up a bit. It doesn't tell you how fast you're going in this exact moment as you're looking at the dash. That number, the one the needle is pointing to, that's what we're really after. Okay, so to really get a grip on that number, we first have to understand why average just doesn't cut it for this job. Let's take a look at the limits of average velocity. Look, average velocity is great for the big picture. It's like the trailer for your trip. It gives you the highlights from start to finish, but it completely smooths over all the details. It hides all the interesting stuff, the speeding up, the slowing down, the moments you were just sitting still. It's a summary, but it's not the actual story. And here's how we calculate it. You just take your final position, subtract your starting position, that's what we call displacement, and you divide it by how long the trip took. It's a simple, super useful idea for a whole journey, but to understand one single instant, we're going to need to dig a little deeper. And that brings us to the really cool part. How in the world do you capture a single moment in time? This is where the magic really starts to happen. The core idea here is actually beautiful in its simplicity. We start with that same average velocity calculation, right? But instead of looking at the whole 5-hour trip, what if we looked at the average over just 1 minute or 1 second? Or even a tenth of a second. We just keep zooming in, making that slice of time smaller and smaller and smaller. Let's try to picture this. Think of a graph where you've got your position on the vertical axis and time on the horizontal. If you draw a straight line from the start of your trip to the end, that line represents your average velocity. It just cuts straight across all the little bumps and curves of your actual real-world motion. Okay, now watch what happens as we start to slide those 2 points on the graph closer and closer to each other. As that time interval gets tiny, the straight line we drew starts to hug the real curve of your motion much more tightly. It's becoming a way better approximation of what was really happening in that smaller and smaller window of time. We keep pushing them closer and closer together until the 2 points are practically sitting right on top of each other. The time between them is infinitesimally small, and at that exact moment, something amazing happens. That line doesn't cut through the curve anymore. It just kisses the curve at one single precise point. It becomes what we call a tangent line. And that right there is our official definition. Instantaneous velocity is what you get when you take the average velocity, but you let the time interval shrink so close to zero it basically becomes a single instant. That whole process, that shrinking to zero, is what mathematicians call taking a limit. So we have this idea of a tangent line on a graph. That's cool, but what does it actually tell us? Let's make this super concrete and see how we can literally read motion right off a graph. Here's the big payoff. The steepness of that tangent line, what we call its slope, is the instantaneous velocity at that exact moment. It's that simple. A really steep positive slope? That means you're moving forward fast. A shallow slope? You're moving slowly. And what about a totally flat, horizontal slope? Well, your position isn't changing, your velocity is zero. Okay, let's walk through a quick example. In this first half second, you can see the position line is going up. If we calculate the slope, rise over run, we find the velocity is a steady positive 1.0 meters per second. Then, from half a second to 1 second, look, the line is totally flat. The slope is zero, which means the object has stopped. Finally, from 1 second to 2 seconds, the line heads down, giving us a negative slope. The velocity is now negative 0.5 meters per second. The object has actually turned around and is going back the other way. Whoa, hold on. That last part, where the velocity became negative, that brings us to a really, really important distinction that trips a lot of people up. So let's take a second and clarify the difference between velocity and speed. This is absolutely key. Velocity is what we call a vector. That's just a fancy way of saying direction matters a lot. That's why it can be positive or negative. It answers the question, how fast and in which direction? Speed, on the other hand, is a scalar. It doesn't care about direction at all, so it's always positive. It just answers one simple question, how fast? Let's make this crystal clear. Imagine 2 cars. One is heading east at 7 meters per second.
We'll call its velocity +7. The other is heading west at 7 meters per second, so its velocity is -7. Because they're going in opposite directions, their velocities are totally different. But what do their speedometers show? They both read the exact same thing, 7.0.
And that's the formal relationship right there. Instantaneous speed is just the magnitude or the absolute value of the instantaneous velocity. You basically just take the velocity and strip away any negative sign. So that number you see on your speedometer, that's your instantaneous speed. So we've gone through this whole process of imagining shrinking time intervals and finding slopes on graphs, which is great for understanding the concept. But, it's a lot of work, right? What if there was a faster way, a kind of cheat code? Well, there is. Let's look at the physicist's shortcut. This is the language physicists use. That entire conceptual journey we just took, of zooming in and finding the slope at a single point, that whole process has a name. It's called taking the derivative. The derivative is the mathematical tool that was literally invented to find rates of instantaneous change. And this is what the notation looks like. Now, when you see dx dt, I know it can look a little intimidating, but don't let it fool you. All it's saying is the instantaneous change in position, x, over an infinitesimally small change in time, t. It is the precise, compact mathematical language for the slope of the position time graph at any point you want. And the power of this shortcut is just incredible. If we happen to know the equation for an object's position over time, we can use a pretty simple rule from calculus to find the equation for its velocity at any moment. So if we want the velocity at exactly 2 seconds, we just plug t = 2 into our new equation, and we get our answer, 9.0 meters per second. No graphs, no shrinking intervals. It's precise, it's fast, and it's honestly pretty elegant. All right, so let's boil this all down. What are the big things to remember? First, average velocity is the big picture, but instantaneous velocity is all about that one specific moment, and you find it by getting the slope of the position graph at that single point. Second, and this is huge, always remember the difference. Velocity includes direction, but speed is just how fast you're going, plain and simple. And that leaves us with one final thought. This idea of an instantaneous rate of change. It is one of the most powerful concepts in all of science. We've applied it to motion, sure, but where else does it show up? I mean, think about the instantaneous rate of a chemical reaction, or the instantaneous growth of a population, or even the moment-to-moment change in the stock market. The physics of right now is absolutely everywhere.